guys for the live streaming on the YouTube. So can everybody give a try using the, let me send a link so that everybody can have it. See if that's actually help everybody get a better signal. If not, then I probably run out of ideas. Okay, the link now. Okay. Okay, so I hope everybody can get it now. Is it good? Are we all set? I'm gonna start teach today's class, okay? Great. So if you have problems, just also type in the, interrupt me or type in the. Okay, so what we have taught in the last lecture is about the phase behavior in general in polymer solution. It is a very important for our polymer class, and if it's not more important. So what is about the phase behaviors tell us if you put two polymer or one polymer in a solution and you're trying to guess if it will be mixed or not. Practically, this is very important in a sense that when you formulate a polymer solution, formulate a polymer coating, or do anything with the polymer, if you don't want to use a melt process, then it will be much better, right? So now you know the importance of it. Now, why people haven't studied a lot of it? In a basic level, yes, people have done it, and there is a lot of work all the way back in the 1950s, as I talked about Flory-Hagen theory. Flory-Hagen theory is one of the greatest examples that people use the polymer physics to understand the phase behavior. There's a lot of assumption. Again, I'm going to give you a fair good amount of warning that they might sound non-realistic, but they already did a very great job in predicting the phase diagram. In other words, if I have a polymer, a solution, if I add them together, and I can already predict what their phase behavior means at what temperature and what amount of the solvent content, I can tell you if it will be mixed or not. That's quite amazing. From a science point of view, I am very pleased to know this is even feasible at the beginning. But now you see it, and you saw some of the early days where in the last class where we have talked about this phase diagram for a polymer. So let's go back. This is, again, I want to remind everybody, this is the phase diagram what we have talked about. You have basically something called a homo-lumo, not a homo, UCST and LCST behavior of your solution. Those two are very common, where you describe what is phi is a polymer concentration, T is a temperature, and you can use UCST and LCST to describe a lot of behavior of your polymer solution. So today's lecture.
I think
there's a question. Yeah, Makita, please.
Yeah. So the two audios are like super off. And it might be easier if you were able to like mute yourself on Zoom, maybe, and then we could just listen on YouTube.
Yeah.
And then we could still have this chat, perhaps.
Yeah, that's great. You can do that. You can actually let's do that. I'll just mute myself. If you have a problem, just call out and I can hear you guys.
Okay, thank you.
All right, now I'm muted. So it's a little bit technical sorting at the beginning, but I think we're getting better. So now it comes back to what we have left about in last lecture is talk about, now I have a way to plot what is delta G, which is free energy, with respect to what is a volume fraction x2. This would allow us to now get something called delta G, energy landscape. So think about the words landscape. What is landscape? Landscape is something you go out, for example, to the west. Not necessarily in Hattiesburg, it's fairly flat here, but if you go to the Wild West, go to Yosemite, Zion National Park, you will see there's up and downs in the landscape, right? There's mountains and there's a valley part of it. So this is pretty much like that. This is a landscape for the energy. You have the peak for the energy, you have the valley for the energy, you have different parts. So this shape of delta G will determine what is the phase behavior of your polymer. Okay? So listen carefully, that the shape of the delta G will determine the phase diagram. So what do you see in the phase diagram is all originated from this particular delta G map. So that comes down to today's lecture. What we're going to do in today's lecture is to teach everybody how to connect a delta G versus concentration map, as you see here, to the phase diagram we showed in the last slides, where you can observe a UCST or LCST behavior. And we talked about briefly how do we determine if a phase separation will happen spontaneous or not. And that's very easy, where if you can kind of assume, if you have a solution sitting right here, if this is a beak of solvent, if it will phase separate, then it will go into a region where is a low in concentration and a region is high in concentration. So we just need to understand that if the solvent after phase separation, does it have a raise in delta G, which is denoted M star, versus where it's beginning with denoted with M. So if your phase separation result in energy increase in the system, then this is not favored, which is showing particularly this phase diagram. Although you can see there is a region that will have lower energy in delta G, it's not sitting in the lowest energy landscape. But please, you cannot assume this is going to be just go down, because you cannot magically shed some of the polymers in X2. The conservation mass tells you you cannot lose anything, right? If you're going to lose something here, you're going to gain some of the polymer in another solvent in the same beaker in another region. They're locally phase separated, but they need to be conserving the mass. So that's why we're always going to have this phase separated region. You have a high and a low region, okay? So with that, next we're going to talk about is what's the criteria to determine it will phase separate or not. So, and we talked about using the second derivative of delta G. Basically it says if your curve is concave up or concave down, will determine it will be stable or not. So let's talk about the phase separation process and something called leveling rule. So what is the lever rule basically says is when you're going to phase separate, it's not going to be phase separated into usually a pure a solvent phase and polymer phase. Usually not that extreme. There are several reasons behind that. So a lot of time you actually will phase separate into just the two phase. One is you have less concentrated polymer, okay, which is shown here, and the other is more concentrated. we call it polymer rich phase, and there is a polymer poor phase. And we can just simply call them alpha and beta in order to make them easy to be described. So example is shown here where we have alpha phase and beta phase. In the alpha phase, you have some polymer, and as I mentioned, it's not a pure solvent. Otherwise, you wouldn't have any polymer in it. And you have a beta phase where it's rich in polymer. That means it will be higher than where you start off. So if you look at here, you can see we sort of give you an example where we can talk about phi 1, which is a solvents, and you can see the solvent's going to be richer in the phi 1, and phi 1 means 1 is solvent, so phi 1 alpha is getting increased in concentration, and phi 2 is lower. And this is pretty much what we talked about in the last lecture, that your amount of the solvent and the polymer before and after phase separation need to be fixed. What this means? This basically says that your phi 1 would be equal to F1 alpha, phi 1 alpha plus F1 beta, phi 1 beta. This is basically a leveling rule. The concentration of phi 1 multiplied by how much phi 1. F1 is just how much volume you had in the phase separate region. Let's say if you have 1 ml of polymer in toluene, you're going to phase separate, and you might have 0.7 ml of lower concentration, 0.7 ml of high concentration. But adding together F1 alpha, F1 beta should be 1. Okay? And delta G, again, is a linear combination of G alpha, G beta, and adding them together linearly at the point where it's phi 1 going to give you G alpha beta, and this would be G mix. That would be before if you have phase separation. That would be this data point. Let me mark it. This would be the after. This would be the before. So you now can see that you have a before and after. So this would be the before if we phase separate. This would be after we phase separate. And you can see the gap is basically, again, like I mentioned, the energy difference. But now we give you a more detailed equation. You can see how we can understand what is phi 1 delta G alpha beta, F1 alpha, F1 beta. How do we actually calculate out a different region of phase separation and what the value would be? Okay? So the leveling rule would give you some idea, but you can see it's not necessary it has to be phase separate into these two. They can phase separate into this way, and they can separate into many different ways. In the last case, we talked about this would not allow spontaneous phase separation, because after we mixed them, it will not likely to be phase separate again. But in this case, the after and before energy is different, where you can see now the curve is concave down. What that means, if I'm sitting here, I wouldn't go up, but I would go down. If I'm starting here, I could phase separate into the G alpha, G beta. Okay? But you cannot go this way from low energy to high energy. In other words, if I now prepare a solution of these two into two separate beakers, and I'm trying to dump into one, they will not mix. Why? Because in this case, before mixing energy is where it shows here, and after mixing, it needs to be raised to match this line, which is not the case. Okay? So this gives you some idea what the criteria would be phase separating and what criteria will not. And it's pretty much already given by the Flory-Huggins law. If you can understand the Flory-Huggins theory very well, and you can plot the delta G versus with respect to the phi, and you can get this pretty much this curve. And you can do that with some help of the computer. You can ask computer to get the G energy, free energy, with respect to 0.015, 0.02. You can calculate out a series of dots, then connect them. Okay? So next one is where we're going to talk about.
Okay. I found this on the web for a series of dogman connected. Check it out.
No, come on. Siri is too sensitive. No Siri, okay? So now phase behavior. We're now going to talk about solution phase behavior, and this is where we talked about what is delta S and delta H contribution. We have discussed many times, and let's look at it one more time. What would be the contribution of delta S of mixing? And again, we're going to start with the regular solution theory. You would see that you have R, x1 log x1, x2 log x2, and we know this is the number fraction of what is your solvent A molecular, and this is a number fraction of your solvent B. If you assume they occupy the same amount of volume for each molecule, these are also you can understand there as a volume fraction as well. So by plotting the data there, you can calculate out what is delta S divided by R is, and it's only going to be simply given as a minus sign, x1 log x1, x2 log x2. So if you plot based on the data, put in all the x1 results, x1 is just a number. You can plug in all different x1, and quite simply, if you put the x1 as 0 or 1, there's no mixing, so there's no delta S. And the mixing in terms of entropy, if it's 50-50 blend ratio, then this will be the highest. Where x1, x2 both equals to 0.5, you would be able to get where delta S divided by R would be somewhere at a number of 0.6. Okay. This would be the shape of delta S. How about delta H? Here it's going to be slightly different. We need to consider delta H divided by RT, okay? So in this case, what you're comparing is delta H divided by RT, where delta S is only delta S divided by R. So there is a difference here I want to first point your attention to. In one case, it has a temperature turn, the other is not. And we will come back to this point in a moment. Now, as you see, the entropy contribution now depends on what is sign of the chi and what is x1, x2 value. And let's assume chi is 0, then this will be not dependent on x1, x2. Then you would end up with a flat line. If you assume chi is 0.5, and you will be able to see x1, x2 is just going to be a curve shown here. And you can easily get it, right? And so chi is now determining what's the shape of this particular parabolic curve. If the chi is positive in a very large value, you would have ended up with this very much parabolic curve, okay? You guys got it? So this is going to be showing you what is the delta H mixing in terms of lattice series. So now you can combine these two to get the delta G. Combine the delta H, combine the delta S, and combine the delta H. So if I just simply add them together, using the value I gave you guys, I would get a curve look like this if I use delta G equals to delta H minus RT, okay? So if your chi is 0, which means there is going to be a flat line with delta H, then my my delta G is only going to be the negative mirror of what we show in delta S. So if you look at this particular curve I boxed using a red square here, this will be a direct mirror of what this delta S is, except this is from 0 to somewhere between 0.62. Now, if I take a delta H minus T delta S, this is what you're going to get. But remember, we need to get a unit, right? So this is going to be delta G divided by RT. Okay? So, if now our chi value goes up, if it's 0.5, this is the difference in the enthalpy. If you look at this is reference line, so your enthalpy has some contribution, but most of the delta G is still negative. There's no changing in the slope of the line or second derivative of delta G. It's all going to be negative. It's going to be parabolic is with a bow shape, and a bow is pointing upwards, right? Both these two. So if your chi is now getting bigger and bigger, as you will see, that at some point your magnitude of the enthalpy term will be bigger than the entropy. If I have to put an entropy term here, I'm going to just copy the one on the left, and you will be able to see using a dashed line. So if you have delta H have the chi value will be much bigger than 2.5, then you would have a potential to induce a term that is chi is bigger than delta H. And this is going to be shown here. Now, adding these two together, you will see at the beginning you would have a local minima, okay? Even with chi equals to 3.5, this is where you would get a small dip, then it's going to go up. Same for chi equals 2.5, you would get there is not necessarily there's not necessarily as obvious as that one, but you can have a local minima and then the curve start to come up. Okay, so you can see how chi could influence this delta G curve. The changes of magnitude of chi value directly influenced the magnitude of this particularly delta G. Okay? And that's where the magic going to begin. As we defined what is the criteria for it to spontaneous phase separate, that will determine if your phase will be stable or not. So you will be able to tell there is several different regions. There are regions that your curve is going to be stable. That's where you'll take a second derivative of delta G. And define what the sign of it. If it's going to be a positive sign, for example, those two curves where it's curving up, then you can claim this is a case where you have the material or the solution is very stable. But these two are easy to understand. Chi equals to 0, chi equals to 0.5. But how about chi equals to 2.5? That's where things getting a little bit tricky. That you now be able to take a second derivative, and you will see there are going to be regions changing sign. And this region where I marked going to be less than 0 in the center, but there's a region it will be larger than 0. What this means is now you created a delta G energy landscape have included two regions of stability of the phase diagram. On the very far end, between let's say phi equals to x or phi equals to from 0 to 0.1, you have the region where you have the curve is the bowl shape of the concave is pointing upward, that means it's stable. So you can have a very homogeneous mixing, and phase separation is not spontaneously allowed in here and here on both sides. But whenever you're sitting in the center, then if you have phase separate, we know that's now allowed it, because you're going to phase separate into an alpha phase and beta phase, and even we combine these two energy, it will be lower. And when the chi is even bigger, then you would have a more obvious, but now your region is being pushed more to the side, where as I marked the crossover point, you're going to take a second derivative of delta G with x. And this will be marked the transition point where you go from stable to non-stable state, okay? So, very good. The phase diagram of the regular lattice series will give a lot of knowledge already to understand what actually drives the material to spontaneous phase separation and what it is not. And simply, fundamentally, it's just determined by delta G's landscape. Whatever local shape of your delta G will determine ultimately if your phase will be stable or not. But fundamental level, why they would matter is coming down to entropy and enthalpy, as we discussed here. Entropy is relatively always going to be negative value, promotes mixing, and enthalpy is now depending on the sign of the chi. If the chi is very large, then your enthalpy could overwhelm the entropy and now start create local regions that is not stable. And please note that it's not necessary we have to get absolute value of delta G. We're not aiming for you have to have a positive delta G so make it unstable. Really, we are looking at the second derivative of delta G. What I specifically mean is if you look at this chi equals to 0.5, you have a line that is show delta G is 0. That means this would be an imaginary line if I have to draw it. Let me put it on here. This red line. But as you can see, even that chi equals 2.5, there's a lot of data point is below and is negative, but it does not mean your material will be stable. Okay? In this, your material will still be able to, if I sit here, I will still be able to phase separate into these two regions and create imaginary mixing energy will be lower than what we start off, then I would phase separate happily. Okay? So in the Flory-Hagen theory, it will be very similar to what we talked about, but except that we know the Flory-Hagen theory differs in the solution theory, that the entropy term is now different. The entropy of the polymer's contribution will be much lower. So as we show here, this is a delta G mix in terms of a Flory-Hagen theory. You have mixing entropy of the solvent, mixing entropy contribution of the polymer, and the enthalpy contribution. And so one of the major obvious thing you will see is the phase diagram is no longer symmetric because of delta G and because of this dP or N contribution to our Flory-Hagen theory. So in the last lecture we see that all the data is symmetric. That means it's always mirrored at x1 equals to 0.5, but now it's not, and the curve is skewed into one direction than the other. Okay, so but it does not change the way how we interpret the data and the definition or understanding if the polymer and solvent will phase separate or they will stay mixed phase is again can be understood through the second derivative of delta G with respect to the, in this case, not x, but we can use a new term phi here. Okay? And this defines if it's larger than 0, or if it's smaller than 0, will determine if we'll phase separate or not. If it's larger than 0, that means it's stable. if it's delta G is smaller than 0, then it's going to be spontaneous phase separation. Okay? And we will see that in the data, if we have low molecular n equals to phi, and most of the region is, if you take a second derivative, it will be O positive. That means it will be stable. If you have n equals to 500, then you will see there's a tiny region maybe around here that is not stable, and you would have phase separation. Okay? If you have more complex case where you have now two polymer melt is mixed with respect to each other, then as we know that you would be able to calculate out what is entropy contribution for species A polymer and species B polymer, and as shown here, defined by the N1 and N2 degree of polymerization and chi prime meter. Okay? So then the phase diagram is now depend on the shape of what is the value of N1 divided by N2. And this will determine how does the phase diagram will be more favored during the entropy of the mixing for which polymer. And the lower the molecular weight or lower the dP, it will contribute more into the entropy. So if you have lowest molecular weight, if you take an extreme case, if n equals to 1, then you simplify this particular binary blends of the polymer back into polymer solution in solvents, if you define one of the polymer as solvent when n equals to 1. But let's take a look at it. If n equals to 1 and chi, again, you will realize why chi is very small, because if any large chi value, then you would phase separate. There's not much entropy contribution because it's all going to be divided by a factor of dP. So your chi need to be very small to match the magnitude. If you have a chi equals to like 0.5, this will not be mixing at all to begin with. So here, now let's look at if they will phase separate or not. Then you would see n equals to, there's a scenario n1 divided by n2 equals to 1. You have scenario n1 divided by n2 equals to 0.5. And you will see, depending on which one has high molecular weight, then it will be skewed into one direction than the other. Okay? So pretty much like what we saw in the last class. And if you take a second derivative, you can see there's a point where, for example, take the green one, they're likely these two regions can define the transition point. Before that, it's going to be stable because this is going to be a parabolic curve concave up, and this is going to be the curve pointing down, right? And so now comes back to what we can discuss is where this is a derivative of free energy. So we have to see opposite cases where one is with the curve with a concave up, and that means if you have phase separation, it will increase the free energy of the system. And any mixing state has a lower free energy than the blend two would phase separate into, right? So that means it's going to be very stable. And there's a curve that means it will concave down. And I summarized then here as one case concave up, one case concave down, but pay attention to what we are plotting, delta G versus respect to the phase, okay? This is going to always make the material is in the example we show here. Where on the concave down case where we tend to phase separate, this tends to be stable. Again, there is whenever there's display, there's always since a conversion between the PC and the Mac. Okay. So you know that second derivative, if it's larger than 0, it's stable. If it's smaller than 0, then it's not stable locally. And what is a derivative means? Let's give you guys an example. So this blue one, let's assume this is going to be just an example curve shows in blue. the second derivative is going to give you, the first derivative going to be show as green, and second will show as you as the other color. And in the case we define it's concave up or concave 1, we determine by the data point that is passing 0. So in other words, I can mark 2 data points that you have the transition point. Okay? Usually those corresponding to the highest slope in the blue curve, not the green curve. Okay? So the blue curve, you can see this region going to be concave down and this going to be concave up. Secondary, or the reds are positive value or the reds are negative value for the blue curve between these regions. It doesn't matter if how negative or how positive it is. It's all going to be the same as long as it has a sign of positive or negative. Okay? So what is we mean by locally stable? The phase behavior, and what is being by locally stable? The definition is very interesting. Locally stable talks about the concept that when the polymer is dissolved in the solution, if there is some local disturbance in the energy, then will it be able to maintain or not? That's a question. And fluctuation always happen no matter where it is in the homogeneous solution. On the outside, it looks like very homogeneous. Like if you have a toluene dissolved, polystyrene dissolved in toluene in a beaker, if you look from outside, it's always going to be a transparent toluene. But inside, if you have very cool, powerful magnifying glass, you can really zoom in and start looking at what's happening at molecular level. The polymer chain will behave like a Brownian motion, so it's going to diffuse around, and this motion of the polymer creates something we call a localized energy, a concentration fluctuation. At a very local level, on the order of few angstrom, few nanometers, then you could have a region that sometimes is high in energy, sometimes in lower in energy. And these energy, what we call it is deviation from the concentration. So what we show here, if the dashed line is ideal concentration, it's a macroscopic concentration where we dissolve or where we prepared. Let's say 10 milligrams per ml is what this curve. So now you zoom in, you have a magnifying glass, you zoom in by a factor of 10, it's going to still be stable. But if you keep zooming in at the molecular, as I mentioned, at single chain level, then when the chain enter and exit that specific volume, let's say a few a nanometer cubical, you could have a chain enter this region, shows in the blue curve, there's going to be a spike in the concentration, and equally there are going to be some region that lose your particular polymer chain. And depending on the position and because of diffusion motion, you're necessarily always going to have this fluctuation in the concentration. And this fluctuation and give phenomenon to the light scattering, as you will see and learn in the next class with Dr. Yung Simon. But this perturbation will result in several important phenomena, like what I showed everybody in the stable of my my remote. There's 3 different cases. There's stable, unstable, and metastable. Unstable case, we don't need to cause any energy. It will spontaneously relax and phase separate. But in the case of metastable, so if I hold this vertically, metastable means that my remote, if it's leave there, it will be very happy. But if there's perturbation or fluctuation in energy, it might be that it can break a metastable state and relax into even lower energy state. So the fluctuation and the degree of fluctuation is important, which we will see throughout this discussion. If you are in a metastable state, it's potentially it can be stable, but you cannot introduce any external forces or stimulation allow this to continue to phase separate. Okay, so we're going to talk about one more thing, and we're going to talk about how do we derive the phase diagram from delta G to temperature versus phi. And here we already show that first we know what is definition of second derivative of the phi. That means there are going to be regions that your polymer chain will not be able to stay. That is unstable region. So if I'm giving a random delta G energy diagram as shown in this black curve, okay, now I'm going to go a bit slower. So you would be able to define here and here as two different regions. As I marked it with cross, and I'm going to make it bigger. If I take second derivative, when this equals to 0, I can find two data points right here. And these, on the left of these, are going to be delta G, second derivative larger than 0. That means these are going to be stable. In the middle, this is going to be a negative value. This means this is going to be unstable state. And this is going to be another stable state. So now, this means in this particular phase diagram, I can plot regions where this will spontaneously phase separate and form two phases in the center. What I highlight in this light blue color, so this is going to be the two-phase case. And these two are going to be the one-phase case. Okay? And the other thing that we need to consider is where the minima of the curve. What does the significance of the minima? So the minima, as you can see, the local minima is just to tell you where this tends to be the lowest is the energy of that particular point, right? But the question is, if we want to phase separate, there's a few requirements we need to take. If I am at data point A, if I want to phase separate, I know that I'm sitting on A is not necessarily stable. But now when I phase separate, I can actually get into different ways to distributing my phase separate region. I can have the phase separate into the B case scenario. I can phase separate one to here, one to there. That's a possibility because I can basically shed some of my molecular into reach the lower concentration point on the left, and the rest I need to push into the high concentration point. So that's a valid conservation of the mass scenario. Okay. We know it's going to phase separate. The second question is what would be the phase separation at the end of the degree of phase separation? What that mean by, well, they phase separate, let's again use the 50-50 roughly here, okay? Where they phase separate into 40-60 or 30-70. There's many combinations now I can draw, right? So which one would be the right one, and which one will be actually system will be equalized at the end, okay? So this is where we're going to discuss where the most stable composition, and that is where we're going to reach the minimal energy around this curve, okay? Here, D point and E point. It's not necessary it will be the lowest energy point. It may looks like it is, but it's actually is the tangent from this red line to intercept this black line. That's where the definition of the D, and that's where the definition of E. Okay, and don't directly understand this would be in minimal point. So let me zoom in, make it really big. Your minimal point would be absolutely there, but your tangent point will be slightly different if you approach with another line, okay? And why this is significant? Because if you draw all the possible scenario, this line, this red and this dashed line would intercept that lowest possible data point along this delta G drop. In other words, if you take this approach, that's a delta G drop you could have, as my two fingers is pointing at. If you take either the green scenario or the blue scenario, that's the energy delta G drop you can have in terms of phase separation. So we know that this is going to be the most favored phase separation for the system. And that defines, if you phase separate, what will be the phases if they are between the rich phase and poor phase. And this is going to be the poor phase for the polymer, as phi 1 will be lower than where we start off. And this will be the rich phase for the polymer, as the phi will be bigger. Okay? And we can do this through the chemical potential approach. What this means is we need to make sure the chemical potential for your polymer is going to be reached at two different regions in two different phases. What this means is the chemical potential for this polymer in alpha phase will need to be equal to the chemical potential in the beta phase. Okay? As long as this second requirement is met, then your system is stable. There is no driving force for it to change. And this can be simplified using the particular equation as we show here, where we need to utilize a molar change in the free energy, and that's what we already defined. That's what where the molar energy is chemical potential. Molar energy is delta G. Take a partial derivative to the number of moles. So if you have molar energy multiplied by the number of moles, that's corresponding to delta G as well. What this means is where your molar energy will behave like an intercept, where you can define what is delta mu1 and delta mu2. These two are intercept at the y-axis when x1 equals to 0 and y-axis equal to 1. Okay? So again, this is just another mini requirement when you phase separation would need to be understood from your chemical potential perspective. Okay, so I think this is about the time, because we about 50 minutes into the class. I'm going to stop here, and in the next class we're going to wrap this up. Well, there's a couple other terms I'm going to first fast forward to define and help everybody to understand in the next class. In the next class we're going to jump into the phase diagram, and I will explain what this is. This is plot as temperature T versus respect to phi 2. So this tells you now you can use the Flory-Hagen theory and delta G free energy diagram. Now predict when your polymer chain will be phase separate, when they will be mixed, and when they will be metastable. So for example, in this particular curve, we know that there is area we call one phase, and this is where outside this curve is. Your polymer chain is always going to be dissolved very well. And there's regions where you're going to have two phases where your polymer chain will phase separate always into two. So if I want to formulate a new chemical product that my manager asked me to do, I definitely want to refer to this curve. If I mix 20% of polymer into the solution, I certainly cannot go from low temperature because it's in the metastable state. I need to go at least above this critical temperature to reach into this one phase. Okay? And that's where we're going to go in the next lecture. So now I'm going to first stop the YouTube live cast, and I'll leave a few minutes in the Zoom for everybody to ask me questions. So let's gather together one more time in the Zoom, and feel free to use the next few minutes.